So you want to just remember from pre-calc that if you have a function, I'm just going to use x over 3, then the period is 2 pi over b, where b is a third. Right? If we have a general cosine or sine function, the natural period is 2 pi, and then if we scale the x-axis by a factor of b, the period is then going to stretch by 2 pi over that. So our period here is going to be 2 pi over a third, so 6 pi.
Yeah,
So
but
for
when
that
I
particular,
tried,
sorry, what you say?
so when I tried it on Desmos using polar coordinates, it was finishing a cycle after 3 pi. So I was wondering how that happens. I already knew that it was going to be 6 pi, but when I graphed it using the polar coordinate, it came out to be 3 pi.
What do you mean by graphing it using the polar coordinate? Just changing that x to a theta?
So I put in r equals sine cubed whatever theta over 3 in the Desmos, and yeah, like it drew like kind of like heart shape.
Because it might loop over itself just because of the radius. I see. That might be right. Let's pull it in the polar. Yeah, so we get a... Yep. Okay, so let's go over graphing it then. Because if it's a polar curve, yeah, it's not that the period is different, it's just that the full loop is going to be different. So we've seen a few examples of this where, like, whenever you're graphing like r is equal to cosine theta or r is equal to sine theta, we've seen how it creates a circle, right? But that circle is actually created in half the period. So weird things can happen where, even though naturally the function has a period of 6 pi, because on part of that period, as we saw with, if we were just trying to graphing it linearly as f of x is sine cubed x over 3, part of the graph is below the x-axis, namely that it's negative. So if we were to actually try to graph that in polar coordinates, r is equal to sine cubed theta over 3, well, what's that going to mean? That essentially means that for the second half, so to speak, of the natural period from 3 pi to 6 pi, the radius is actually going to be negative. And so if we're getting, in some sense, the opposite angles from 3 pi to 6 pi, and the radius is negative, we're kind of tracing over the curve twice from doing that. So the way you want to go about stuff like this, especially in polar coordinates, is always just draw the graph. And so always draw the graph and start at 0. And so we've got our table, start at 0. And so far when we've been doing these, start at 0 and go up to pi. See what you get, and then see what happens if you keep going.
What values for theta would you choose? Because it has like 3 on the denominator. It's kind of
Yeah,
tough.
great question. That's actually the next point we need to address. So normally what we want is, I like to put in values of pi over 4. So that's what we've been doing for all these other examples, just because graphing it sort of every pi over 4 angles makes it a bit easier. But when you change the divided by 3, you want to make sure that you're choosing angles that you can compute, really, is what you're trying to look for. So pi over 4 may not be the best. Let's take a look and see what happens. So almost universally, I like to start with these values when I graph it. Just because the theta is always going to be determining the angle. So we start always at 0, then we've got a point at pi over 4, we've got a point pointing vertically, and those are easy angles to eyeball, to draw, and then you can calculate the radius and figure out where you are on that radius. The problem is maybe we can't actually compute that for some of these. So start, if you can't compute some of them, maybe just leave those there and then go back to it and try to get a sense of the graph based off of the other values you're calculating. So for example, we plug in 0, that one's easy enough. We are at 0. Pi over 4 is going to be weird because now we've got to compute sine of pi over 12 and then cube that. So you can compute that. Sine of pi over 12, we can compute sine of pi over 6. And since pi over 12 is half angle of that, we can compute that by hand if we wanted to. But we got to use half angle formula, and then we got to cube that. So let's just kind of leave that one off for a second. Graphing, you don't want to spend too much time on graphing these, especially on an exam or a quiz, just because if plotting these points and computing the values takes up all your time, you're not going to be able to do any of the calculus on it that you still have to do. So let's just keep that for a second. We'll say sine of pi over 12 cubed, whatever that is. Maybe we can eyeball it or estimate it from the rest of the graph. When we get to pi over 2, we'll have sine cubed of pi over 6. So that we can compute. Pi over 6, sine of pi over 6 is going to give us 1/2 cubed will give us 1/8. So not big. It's going to be pretty tiny. So maybe here is going to be our 1/8. And we're pointing vertically. And this can give us some sense, well, what is pi over 12 going to be? Sine starts at 0, then it's going to increase, right, to pi over 2. Pi over 2 is where typically sine will reach its max. Of course, we're changing the period a little bit. But we do know that sine is an increasing function. So that sine of pi over 12 should be less than 1/2, and then we're cubing it. So it's going to be, the distance is going to be smaller than that distance. But we do know it's at least positive as well. So that when we're pointing in the pi over 4 direction, I'm going a positive distance in that direction. So it'll probably come out somewhere there-ish, and then that the path will go like that. And then we keep going. Unfortunately, with all of the pi over 4s, those angles we're not going to be able to compute very well, because we'll get sine cubed of, well, no, that one we can, I guess, since we're dividing by 3. That'll be pi over 4, which will be root 2 over 2 cubed. So 2 root 2 over 8, or root 2 over 4. Again, hard to compute, hard to really get a sense of how big that is. But we know that sine itself is increasing between 0 and pi over 4. And since this is changing the natural period, now it's going to be increasing between 0 and, in this case, it's going to be 3 pi over 2. Because we know that if I plug in 3 pi over 2 here, that's when the argument will be pi over 2. So at least up until we get to 3 pi over 2, we know these values are going to be increasing. And so I don't think we want kind of loop downward, but it's going to kind of come up and then go around. And so we've got pi. The next one would be 5 pi over 4, but 5 pi over 4 we're not going to be able to plot. So let's just go ahead and jump to 3 pi over 2. And when we have 3 pi over 2, that'll give us sine cubed pi over 2.
You could plot pi over 3 too.
Pi over 3, that would give us sine of pi over 9, would it not?
No, because on the sheet you have pi, but since it's theta divided by 3, it's gonna be pi over 3.
Oh, that one. Yeah, I just skipped over that one. Yep, you can compute that one. So root 3 over 2 cubed. 3 root 3 over 8. So pi will be over there. One of the key things to kind of recognize is just at least the growth of these values, even if you don't want to compute them and try to estimate how large they actually are. Again, key thing is kind of determining when the values are going to be increasing. Since we know that the radius is going to be increasing up until 3 pi over 2, it's going to look like a spiral. So as we go around, it's going to keep getting bigger and bigger. The radius, the distance from the origin, is going to be getting bigger and bigger up until 3 pi over 2. And then what's going to happen between 3 pi over 2 and 3 pi, it's going to be decreasing. So it's going to, and how does sine behave? Well, if we kept going, essentially all of the values would now repeat, but going in decreasing order. Because we've got 3 pi over 2, and if we did 2 pi, that'll give us a sine cubed of 2 pi over 3, which sine is going to be positive in the second quadrant, and it'll give us that same value. And so kind of recognizing that here at 2 pi, it's going to be the same as that value. Gives you that piece. And then since we're going in reverse, you kind of got to want to just do that same loop in reverse, except now going around this way. And that's what gives us that symmetry. Of that heart. So overall, determining the period, especially with something like this, where we had the period divided by 3, these pi over 4 values may not have even been worth computing, or like after you kind of saw a couple of them, I didn't keep writing them. Recognizing symmetry, being able to recognize, naturally when sine is increasing and decreasing based off of a period shift, and then applying that and applying your knowledge of trig functions and their periodicity now with polar coordinates, we know that these values are going to repeat. And so you can kind of just keep going. I would keep going with, periods of pi over 2. So the next one might be 5 pi over 2, and then 3 pi. and then figuring out those values and kind of estimating and realizing that at 3 pi is when the full period length completes, or at least we've completed one full cycle of this object.
So then you would bound it from 0 to 3 pi.
Yeah,
I'm
so
not
for this one, use
mistaken.
0 to 3 pi. So I think I just naively put 0 to 2 pi in the problem yesterday when we were getting it started. That's because I wasn't taking a look at the divided by 3. Naturally, if we see trig functions and they don't bound it and we want one cycle, your first guess should be 0 to 2 pi. But then as you work it out and graph it, if you see a different period, adjust it.
Would the bounds be given on the test?
Yeah. Personally, I don't like that problem as it's written. I mean, it's fine for a homework problem. I think the other thing with homework problems is we naturally assume that you guys are going to look this up and you're going to graph it on Desmos and you're going to use some calculator tips. So you can kind of guess 0 to 3 pi. If we're having you find arc length on the final, whether it's a parameterization or something like this, the period should be either given to you or it should be like very natural. You should be able to figure it out at least more easily than this guy.
Thank you.
So catching up on chat, sounds like everyone wants some more physics and works problems on the final. I mean, we can make that happen if you guys want it. Which ones were your favorite? The dam questions? Yeah, I think hydrostatic pressure is kind of the weirdest ones. To me, hydrostatic pressure, it's not as intuitive as work. Work is, it's like force times distance. And so you can always kind of break it down. Hydrostatic pressure, deriving that formula, it's a little weird because you kind of got to, like, you got to think about depth and then you got to think the water pressure on all sides and then kind of divide things up. Integration by parts problems, I don't think you guys would want that. Integration by parts takes forever.
How important do you think the questions will be where it's like the Taylor series, but you have to multiply a bunch of stuff together, like divide?
Oh, you mean multiplying and dividing a full Taylor series?
Yeah, like, yeah, I guess that's pretty much it. Do you think it's gonna be super important?
Not terribly important. I would say the basic manipulations are going to be more important, like knowing how to integrate and derive Taylor series as well as multiply by like certain polynomials. Those are more of the basic manipulations of Taylor series and power series, and I think those are far more important.
Okay,
Yeah.
good. So not the thing where you like had each thing on like a line and then you either like added it or subtracted it.
Right. Yeah, like the long division.
Yeah, that was what I'm talking about.
Those you should know. It's going to be hard to put that on a final, especially because our final is only an hour and a half. Like if you do one of those problems, it'll take you 30 minutes. So not terribly important.
Okay, dope.
What about Taylor's remainder? I'm trying to it's like, I guess finding the xi. It's like, what value should you use for the fraction and then what value should you use for the x minus a? Like, is there a certain way you do that? Because I always somehow get it wrong and it just confuses me.
For Taylor's remainder theorem?
Yeah.
Taylor's remainder theorem is weird. Actually, Osita, we were talking the other day, and I guess he said that there was one on the homework that he didn't quite make sense of, at least in terms of what the solution was given. I mean, I don't know. I think he was looking at the solutions to the homework problems, but the solutions weren't working out to what he computed. At least all the problems that I've seen that I've like helped you guys with, they seem reasonable, but I think there might have been some error on the solutions. That didn't quite make sense in that. Taylor's remainder theorem is tricky though, because you've got to find like this maximum x value and this maximum z value as well, which can be different on the interval depending on where it appears.
So for like situations like that, are you trying to, for like, I guess the fraction portion of it, so the one that's like n factorial, do you want that like the smallest value or the largest value given with that situation? Because usually I try going with the lowest since it's going to be squared and then factored.
Let's take a look.
I mean, if you want
So-
an example, I think summer 2019 or 2020.
Oh, good.
has
It's
the
on an
Taylor
exam.
remainders on it.
Okay.
Yeah.
Let's pull that up.
I think it's like question 5.
Let's see. Go to, you said what year? 2020?
Or 2019. I know it's a summer one.
Summer 2019? Let's take a look. Let's see.
Number 4, it's the 2020 summer and it's B. 4B.
$2020 number 4 B. I mean number. Wait, is it summer?
Yeah.
I'm not seeing it. Unless I have.
I could just put it in chat.
Here's my. Yeah, if you want to type it out in chat, summer 2020 exam. Oh, that's exam 1. That's why I'm clicking on the wrong exam. Final exam, summer 2020. There we go. Yeah, use Taylor's formula to estimate the accuracy of the approximation for x in the interval 0.9 to 1.1. Your answer does not need to be simplified. Yeah, so let's write that down real quick. We've got square root of x and Taylor polynomial of degree 3. So how do we do the Taylor approximation for this guy? There's a couple of different ways. We could just go through the actual process of computing the Taylor polynomial, or you could try to manipulate and finagle it from known Taylor polynomials. So you could try to write this, since we're centered at x equals 1, write it as 1 plus x minus 1. And so you could expand this using the binomial formula. If you want. That might be a little harder, especially if you don't know the binomial series and you don't know the formula for the binomial coefficients, especially since we're only computing degree 3. It might be easiest just to compute the derivatives. And maybe it might be easier even to use fractional exponents. and then evaluate at x equals 1. So we'll get 1, 1/2, negative 1/4, and then positive 3/8. So maybe try to line those up when you're making a table or computations like this. And then what's our Taylor polynomial going to be? It's going to be first term plus 1/2 over 2 factorial x minus, no, sorry, I'm off by a degree. 1/2 x minus 1, then now plus minus 1/4 times 1 over 2 factorial x minus 1 squared, and then plus 3/8 1 over 3 factorial times x minus 1 cubed. So your coefficients times 1 over n factorial. That'll give us the Taylor polynomial. And now what do we want? We've got to use the remainders theorem to estimate the accuracy on a tight window. .9 to 1.1. So we give you the formula for the remainder theorem. That is, I don't think that's one we would ever expect you guys to memorize, since I don't know many people, many instructors who they themselves would memorize it. So our Rn is given in the formula sheet. You've got Fn plus 1 of z over n plus 1 factorial, and then x minus a to the n plus 1. So z is between x and a. So when we work this out, what we're going to be computing now is R3, since we have the remainder of our degree 3 Taylor polynomial, is going to depend on the fourth derivative at some point. And of course, we're just plugging in n equals 3 for the rest. So the way you want to go about this is we want to choose x in the interval. To maximize this expression. And I guess we should know, why are we trying to maximize this expression? We're trying to find the maximum amount of error, right? If we want the accuracy on a specific interval, the accuracy is always going to be smaller than the maximum amount of error. So if we find the maximum amount of error, we know that we are at least that accurate. So we're going to choose the x to maximize the expression, and then we're going to choose the z. Choose z between x and 1 that maximizes. Now, it's not always the case, but most oftentimes with these types of problems, since we don't want to murder you guys, the x value that's going to maximize the expression is going to be one of the endpoints. If we had to be proper, then sometimes the x that'll maximize it could be somewhere in between them. Or even worse, the z that maximizes the expression could be somewhere in between there if the derivative has a maximum somewhere within that interval. It's usually hard to do, and problems usually are not written that way, especially if the window that we're looking at to maximize this estimate is going to be only 0.2, right? So at least with x, the x that's going to maximize the expression, well, only depends on x minus 1. So our x can be either 0.9 or 1.1 because we're taking x minus 1 to the 4th. So how do we maximize that? Well, the biggest distance x is going to be from 1 is going to be 0.1 at either endpoint. Doesn't matter. And when I raise 0.1 to the 4th, that'll be the maximum amount of error. And then so what we kind of want to do is figure out, well, what z on this interval, since x can be either end of the interval, we want to figure out what z on the interval will maximize it. And then essentially pick both of those in tandem, pick the x appropriately and pick the z appropriately. So let's take our 4th derivative. So 4th derivative, we had a 3/8 in the last one, so it'll be 3 times 5, 15 over 16. And that one will be negative x to the negative 7/2. And so of course, if we just replace the x with a z, and now we know that our z is somewhere between 0.9 and 1.1, you kind of got to guess and figure out, well, what's going on with this and when is the maximum value. And so this will be maximized when we have the smallest z value. So our overall expression is going to be, and we want the absolute value of it, so the minus sign is going to go away. We'll have a 1 over 4 factorial, is that constant, and then the x we'll choose as that endpoint as well, since technically we need z in between x and 1. So our x 0.9 minus 1 to the 4th, that'll give us a 0.1 overall. So 15 over, and that 9 should have been in the denominator, 0.9 to the 7/2 times 1 over 4 factorial times 0.1 to the 4th. And that expression you won't have to simplify. Any other questions? Review volumes of revolutions, that would be good to review. So there is recitation today. So Lewis is going to take over and he can review with you guys. Any other questions for me? Otherwise, I'll get out of your hair and let you guys keep studying, keep practicing.
Do you have office hours today?
Yes. I think I'm doing office hours 1 to 3.
Okay.
And actually, I can extend that. I should have fairly long office hours. Well, office hours 1 to 3, and then I think I'm also having office hours for my linear algebra class they have an exam tomorrow. But if those office hours aren't too busy, I can open them up to you guys as well.
Awesome. Thank you.